Hello everybody, and thank you so much for being here today. My name is Ioana and I have just finished my first year as a math student at the University of Oxford, more specifically at St. Anne's College. And yeah, it's been quite a ride. From learning a bunch of new and interesting areas of maths to meeting and befriending lots of awesome people, and obviously dealing with quite a lot of self-isolation, there are definitely so many things that I could talk about related to my first year of uni. So in this video I have thought that it would be a nice idea to talk about all the courses that I did this year, all the maths that I learned, and go in depth about the contents of each of them. To spice things up a little, I have also thought that it would be nice to make it a tier list. So I guess what I'll do is just classify all the 17 courses that I took this year based off of how much I have enjoyed the maths involved in them and the way the lectures were presented, which obviously made a huge impact on the way I saw all of these courses. So the categories will be from highest or the best to the lowest or the worst. Could do this forever and still be happy. You feel satisfied when finishing this problem, only doing this because there is an exam in it, and when will I ever use this in real life? So without further ado, let's just get right on with the tier list. At the beginning of my first term at Oxford, we had two introductory courses called Introduction to University Mathematics and Introduction to Complex Numbers. These were set out to basically bring everybody to the same level of basic mathematical knowledge at the start of uni, regardless of the educational system people came from. So Introduction to Uni Maths introduces the precise mathematical language which will be essential for rigorously developing algebra and analysis throughout the first year. There is also some discussion of the foundations of mathematics, the base upon which all mathematics ultimately rests. Then some guidance on how to try and solve problems in pure mathematics, especially the type typically encountered in algebra and analysis in your first year. It was very tedious, the problems involved were quite easy to solve, but required a lot of writing to get to the result, so I guess I would simply just put this into the you feel satisfied when finishing the problem tier. Moving on to the complex numbers intro, this two-lecture course introduces complex numbers from scratch and rapidly develops the theory that we would use throughout the rest of the year. For those of you who are not familiar with complex numbers, these arise when we introduce a new number called I with the property that I squared is -1. We consider numbers of the form a plus b times I, where a and b are real numbers. Using complex numbers obviously allows us to solve the equation x squared plus 1 equals 0. Less obviously allows us to solve any quadratic equation with real or indeed complex coefficients, and not at all obvious allows us to solve any polynomial equation of any degree with complex coefficients. It wasn't something that was that new to me because we went through them quite in depth during high school, but it was very interesting nonetheless, so I think this deserves to be in the could do this forever and still be happy category. Then we moved on to the examinable courses, of which we had 5 or 4, I believe, in each of our 3 terms. So we firstly had Linear Algebra 1. You probably already have one or more strategies for solving a system of two simultaneous linear equations in two variables, such as 3x plus 5y equals 1 and 2x minus 7y equals 10. But what if you had 100 linear equations in 100 variables? Would your strategies generalize to larger systems of simultaneous linear equations? In this course, we met the idea of a matrix, which is a fundamental idea in mathematics. A matrix is simply a rectangular array of numbers, but importantly, we can work with matrices in powerful ways. For example, we can add and multiply matrices. We can record a system of simultaneous linear equations using matrices, and we looked at an efficient strategy for solving a matrix equation of this sort. We saw that matrices can also be used to describe certain geometrical transformations in 2 or 3 dimensions, such as reflections, rotations, and skews. This generalizes to higher dimensions using the abstract idea of a vector space. A vector space is a mathematical object consisting of a set of vectors and a background set of scalars, together with a notion of addition, we can add two vectors, and a notion of scalar multiplication. We can multiply a vector by a scalar. We explore some deep connections between matrices and vector spaces. We define a linear map, which is a nicely behaved map between two vector spaces, and see that linear maps can be represented by matrices. Yeah, there was a lot going on in this course. I enjoyed it, the teaching was great, and it simplified things a lot where needed. But I also think that it was a bit too technical for me, especially in the earlier parts when everything was new and had to be proved from scratch. So yeah, this goes into the only doing this because there's an exam in it tier. We then had, totally unsurprisingly, linear algebra 2. We talked about the determinant, which gives us a criterion of whether a linear map is invertible or not. Then we were asking what directions and which lines are preserved under the map, and more ambitiously whether we can find a basis so that the associated matrix of the linear map is diagonal. In this context, we proved a version of the important spectral theorem that says that any real symmetric square matrix can be diagonalized via an orthogonal change of basis. As a very cool geometrical application, we were able to classify quadratic surfaces in three-dimensional Euclidean space, which was so great and showed us how algebra, which seems so pure, is connected to something very applied, such as geometry. Needless to say, I enjoyed it a lot, and since all the basics from the Linear Algebra 1 course were now assumed to be known, it wasn't technical, so this goes straight into the could do this forever and still be happy tier. We then had groups and group actions. We introduced from first principles a new mathematical object. The crucial properties here are that we can compose two elements and that inverses exist. Ultimately, the importance of groups comes from their actions on geometric objects and other mathematical sets, as for example, the roots of a polynomial. In the second half of the course, we derived the very useful orbit stabilizer theorem and applied it to counting arguments. Basically, a group is one of the more basic mathematical structures which has proved useful and ubiquitous in modern mathematics as well as in its applications, whether it is describing the symmetries of a physical system or that of a crystal. This course has been an entire ride, not gonna lie. It was way too abstract for my liking, but I managed to get through it somehow in the end. Unfortunately, since it was all such first principle based and we had to prove everything from scratch, it was very abstract. I'm going to have to put this into the when will I ever use this in real life tier. We also had analysis 1, sequences and series, which is basically calculus, but on steroids. You start off just by seeing how we add or multiply real numbers, and build up everything there is to know about numbers from scratch. Basically, the idea of a limit is a fundamental one in maths. Precise definitions of limits in different circumstances underpin the area traditionally known as mathematical analysis. The main aim of this course was to define what it means for a sequence of real numbers to converge to a limit and the related notion of a convergent series or infinite sum of real numbers. It was not until around 2 centuries ago that mathematicians succeeded in finding these definitions, which simultaneously fit with our own intuition and lead to rigorous proofs of the properties we expect limits and infinite sums to have. For example, why does 1 over n approach 0 as n gets larger and larger? I absolutely loved this course. The way it was taught was absolutely amazing. The lecturer was awesome, as well as our tutors, so this goes straight up into the could do this forever and still be happy tier. Again, completely unsurprisingly, here comes analysis 2, continuity and differentiability. We pretty much just continue to develop the fundamental theory of the real analysis. We developed in a rigorous way 2 concepts of limits and derivatives for real valued functions of one variable. The core part of the course is then to establish the most important theorems about continuous functions on intervals, including the intermediate value theorem. In the second part, we established the theory of differentiability for functions of one variable, and we employed the tool of derivatives to the study of functions with a very simple idea of looking at special points on the graphs of differentiable functions. We established the major and powerful tool in analysis, the mean value theorem. We proved its substantial applications in deriving other analysis tools, the L'Hopital rule, the identity theorem, Taylor's theorem, and many other useful tools. This was a very heavily proof-based class. Everything had a lot of rigor coming to it, but it was nice seeing where all the most intuitive things come from. So this goes into the you feel satisfied when finishing the problem tier. To keep the chain going, we did analysis 3, integration. So at school one learns how to integrate various simple functions such as polynomials like x squared, x cubed plus x, trigonometric functions such as sine x, and some rational functions such as 1 over x squared plus 1. In this course we take a rigorous look at what it means to integrate a function. Can all functions be integrated? If not, which ones can? This was a lot. It had loads and loads of weird notation, and it took so long to prove things that were apparently so obvious. It wasn't too bad, because by the end of the course I would enjoy doing problems a lot, because it was starting to make sense. But yeah, off in the only doing this because there is an exam in it tier. We then had a course called Introductory Calculus, which lecturers always claim to be the easiest first year course, which it was indeed. Introductory Calculus starts by looking at some techniques for integration and solving ordinary differential equations, and then moves on to look at partial differentiation, which is the differentiation of functions of more than one variable. This then leads on to various methods and applications that may be familiar in the context of one variable, such as finding the maximum or minimum of functions, but which are now viewed in the more general setting of functions of many variables. It had lots of geometrical applications, and the tools we learned in this course proved themselves to be useful in so many different settings, so this goes straight into the could do this forever and still be happy tier. Then we did probability. Probability theory is one of the fastest growing areas of mathematics. Probabilistic methods are used in a tremendous range of applications, from genetics to communication theory, from epidemics to physics to finance. Probability underpins statistics, machine learning, and data science. We explored important concepts such as independence and conditional probability. We met a range of probability distributions and a wide range of probabilistic tools, and developed applications including random walks and branching processes. We proved some fundamental results about the behavior of random processes, such as the weak law of large numbers. It was incredibly well taught, and I enjoyed the course a lot. However, it won't go straight into the top tier, since I struggle a bit to solve probability problems that involve only basic concepts, because these are usually the toughest ones. So yeah, you feel satisfied when finishing the problem. On the same note, we then had statistics and data analysis. So if you were asked to estimate the probability that a particular coin would land heads side up, you would probably be able to estimate that without thinking much about statistical theory. Most would flip the coin n times and count the number of heads, let's say that's x, and consider that x over n was a good estimate of the probability. This is straightforward, but how accurate or precise is this estimation? Are you confident that the probability isn't 0.5? This is the kind of thing that this course was based off on. The course also covers simple linear regression, demonstrating how a linear relationship between two variables, we could just call them x and y, can be quantified. Finally, we gave an overview of the field of unsupervised learning, finding a simplified structure in datasets involving many variables with real-life examples. It was probably the most interesting course we did this year, with real-life examples presented at every proposition, theorem, anything from the course. The problems we got in the exam, however, were pretty difficult, and I appreciate that having such a wide range of applications can lead to very tough problems. So this goes into the you feel satisfied when finishing the problem tier. We then had geometry. This was mostly analytical and vector geometry. Well, the use of coordinates is quite common in mathematics, but are geometric theorems proved using only one set of coordinates, the same as those proved with another set? This directs our attention to notions of isometries and orthogonal matrices. As the course moves on to parameterized surfaces, the same question arises when we change parameters. For example, is surface area invariant under such a change? This was such a great course, and we could always check how our surfaces look like in 3 dimensions on the computer, and it was incredibly satisfying. So yeah, definitely could do this forever and still be happy. We also had a more physics related course called dynamics. We studied Newton's laws of motion, which describe the dynamics of an object in terms of the forces acting on it. The success of Newton's theory hinges on the fact that a small number of very simple force laws, combined with his laws of motion, very accurately describe an enormous array of dynamical problems. For example, in these lectures, we looked at phenomena as diverse as the motion of bodies through fluids, charged particles moving in electromagnetic fields, and the motion of rigid bodies under gravity. A highlight of the course uses the law of universal gravitation to account for the motion of planets around the sun. It was intense. You had to understand a lot of physics going around with the forces acting on your particle, and the calculations were quite involved. To be honest, I have never enjoyed physics, and this will be very ironic, but dynamics goes into the when will I ever use this in real life tier. I'm sorry, but it's where it stands for me. We then studied constructive mathematics, which is all about using effective algorithms in maths and computing. This course serves as an introduction to some of the most famous and useful algorithms across pure and applied mathematics. These have played and continue to play a central role in solving many important practical problems. This course begins with the Euclidean algorithm for computing the highest common factor of integers, which is the main tool for modern data decryption. And it culminates with Newton's method for numerically solving nonlinear equations via gradient descent, which forms the backbone of contemporary machine learning. I love this course. I absolutely loved it. The lectures presented everything very clearly and in a very simple manner, and I always enjoy something that connects math and computer science. So off to the could do this forever and still be happy tier. We then had Multivariable Calculus, which pretty much sits at an intersection between geometry, analysis, topology, and physics. Two main theorems of the course are Stokes' theorem and the divergence theorem. From a pure stance, this can be thought of as 2- and 3-dimensional versions of the fundamental theorem of calculus. But they were theorems first recognized by physicists and were just as important to fluid dynamics or electromagnetism. The course introduces differential operators such as div, grad, and curl. These have physical significance in themselves, but some questions about them lead to topological answers. This was a very difficult course, but once I got the hang of it, I enjoyed it a lot, and I really liked the struggle of getting to a result and finishing a multivariable calculus problem. So yeah, I believe that this deserves to be in the you feel satisfied when finishing the problem tier. The last examinable course we had is Fourier series and PDEs, which stands for partial differential equations. While developing the theory of heat conduction in the early 19th century, Fourier kickstarted a mathematical revolution by claiming that every real-valued function defined on a finite interval could be expanded as an infinite series of elementary trigonometric functions, cosine and sines, which is just absolutely wonderful. The implications of Fourier's claim for practical applications were no less powerful. or far-ranging. The decomposition led to deep and fundamental insights into numerous physical phenomena, for example, mass and heat transport, vibration of elastic media, acoustics and quantum mechanics, and they continue to be exploited today in numerous fields, such as signal processing, approximation theory, and control theory. In this course, we introduce fundamental results for the pointwise convergence of Fourier's infinite trigonometric series. We then followed in Fourier's footsteps by using them to construct solutions to fundamental problems involving the heat equation, the wave equation, and Laplace's equation, the three most important partial differential equations in mathematics, science, and engineering. This was definitely my favorite course. Everything about it was so new and interesting and had so many different applications, so definitely into the could do this forever and still be happy tier. So these were all the courses that we took this year. Besides from this, we also had a module called Computational Mathematics, for which no formal teaching was provided, but we had two projects that we needed to submit in March as assignments, and those counted towards our final grade. This course serves as a first introduction to computer programming, with a particular emphasis on scientific and numerical computation. It goes over finding the best data structures, performing operations on vectors and matrices, numerically solving complicated nonlinear problems or equations, visualizing said solutions, generating and testing conjectures, and implementing algorithms efficiently. We used a software called MATLAB for this course in order to perform all these tasks. All in all, you know I love anything that combines maths and computing, so I should give this a God tier ranking, but I won't actually, because I hated the MATLAB software. They could have gone for much better softwares, and I would have benefited from some introductory lectures in this course. So I think I'll put this into the only doing this because there's an exam in it tier. With that being said, this was everything that I learned during my first year as a math student at the University of Oxford. It's definitely been a lot, and I know so much more maths now than I did before starting uni. As you saw, I enjoyed pretty much everything that we did this year, and I am so grateful that I have been offered the chance to learn all these things at such a wonderful place as Oxford. So yeah, I hope you have enjoyed this video and that you have found it useful. I definitely enjoyed making it. If you did, make sure to give it a thumbs up, subscribe to my channel for more uni related content, and comment down below any video suggestion or any question that you might have. I'll get back to you as soon as I can. Follow me on Instagram for more content if you feel like it. And yeah, good luck with uni, good luck with your mathematical journey, and I hope you stick around for more videos. So I'll see you soon, hopefully. Goodbye.
I'm sick of daydreaming, I just want the feeling of you in my bed. I'm down to just waste time right below your waistline, want you by my head.